We're going to talk about acids and bases now, so we're getting into some actual chemical reactions where we get to see things actually happening. And I've come to understand chemistry to be a lot like the Bible, where every lesson is a long story is this, but it comes with an if and a but and a maybe. There's nothing straightforward in the dang thing. So acids and bases are going to be no different, and I'm going to do the best I can to split this apart for you. The first thing I want to iterate is that acid make plusy, okay? Acids give plusy. Basey give minusy. And I'm writing it this way for a reason, because let's say I have a situation that's balanced out. Let's say I have like 4 positives here and 4 negatives over here and some kind of structure of some kind. It doesn't matter for this particular thing. Now, how do I want to use an acid to make things more plusy? Well, I could add some plusy here, and now in total I have some plus. I have more plus than minus. But what if I just maybe like take this away? What if I just remove a minus? Well, guess what? I'm plusy again. I'm more plusy. So both of those are acids. You see what I'm saying? So if I add positives, okay, that's an acid. I've added positives. But if I remove a negative, where's my green? If I remove negatives, well, I've also created positivity here, haven't I? So that's either one of those things is an acid. Do you see what I'm saying? Now, a base can add electrons and make more minus. Or it can just take pluses away. That makes more minus. Both of those can be a base. So there's like 4 possibilities. You can add minuses, or you can remove minus, or you can add plus and remove plus. 2 of those would be acidic, 2 of those would be basic. So let's look at an example. I hope that that was a little bit fun, because that's about as funny as I can be. The first one that they like to talk about is called a Bronsted Lowry acid. And that adds a hydrogen, which means it's a hydrogen ion, which means it's just a proton. It's a proton. Remember, hydrogen is just one proton in the middle and one electron like this. So if it's an ion and the electron's gone, all you have is the proton here floating around. That's what they mean when they say they add a hydrogen ion. So Bronsted Lowry acid adds plusy. You see what I'm saying? Another one that might be an acid would be something that removes a minus. That's not what this does. This adds a positive. Adds a positive. Let's look at an example of what might do that. Let's see if I brought something together here. Comes from a lovely free website, but I like this a lot. This here is hydrochloric acid and water. And look at the electronegativity clouds, by the way. Do you notice how polar it begins and then how uniform it is in the end? That's an interesting thing to observe. Okay, but this is a Bronsted Lowry acid. Can you spot why? It'll be matched, by the way, by a Bronsted Lowry base, because a Bronsted Lowry base is what accepts the hydrogen ions, so they have to come together. Well, which of these is going to accept the ion and which one's going to lose it? HCl, right here, becomes Cl minus. It lost a proton. It lost a proton, and the chlorine kept both electrons from the sigma bond. So this is clearly going to be the Bronsted Lowry acid. We could just call it the Bronsted acid, I guess. Just smash those names together like 2 particles. And then water over here, which is drawn kind of funny. You see the lone pairs of electrons here? Well, those are going to hover in this direction and in this direction. They're going to form that tetrahedron pyramid shape. You just can't see it. Yeah, but that's what they do. Those lone pairs are up there, so you're going to get your negative space all up in here, which is going to be really interested in this positive space of the hydrochloric acid. That's how they combine. So water is going to take on a hydrogen, and it's going to form a hydronium. And now you see these 3 here. That's the wrong way to draw it. But there's also a lone pair of electrons up here, and that's what forms that same tetrahedral shape. So you still have the same general shape, but for different reasons. It's a little different, but anyway, I want you to notice that oxygen has a +1 formal charge. So when I circle just the local oxygen here, I see 3 bonds and 2 lone electrons. That's only 5, but oxygen, as you know, is number 6 right here in the second energy level. So he is not neutral anymore. He was neutral here, which means the oxygen here has accepted the hydrogen, and that makes it the base. This oxygen is the Bronsted Lowry base within the water, if you want to think of it that way. But we just say that the water is acting as a Bronsted Lowry base, and that it becomes H3O, which is called hydronium. Now, you see that the arrow goes back and forth because when this is resting in water, it goes back and forth all day. These will recombine and form these again too. It's happening constantly, many times per second all over the solution. So it's not like once something forms, it just stays that way. They're in constant flux between each other, depending on a number of conditions. They call this the acid, Bronsted Lowry acid, Bronsted Lowry base. This is the conjugate base, not acid anymore, and this is the conjugate acid. And the reason for that, the reason we call this the conjugate base, is that this is going to accept maybe this hydrogen when it goes backward, which means as the accepting party, it is a base. We call it the conjugate because it just means that it's not the one from the original, and it has to go backwards. So this hydronium will act as the conjugate acid because it's going to give away its hydrogen when it goes back. Okay, that should be pretty straightforward. Let's look at maybe, okay, I've got one for you. Let's take out this one. Okay, this is ethanoic acid, or maybe you know it better as acetic acid. Have you heard of acetic acid before? That's the most common name for it. Look at what we've got going on here. Here's our base. That is an alcohol. OH is an alcohol group, and I want you to notice this oxygen has a -1 formal charge. If I circle the oxygen alone, I can see that there's a bond and 6 electrons. That's 7, so that's 1 too many. That's what makes it a -1. And then I'm going to combine it with acetic acid, and I want you to notice something here. This is an alcohol functional group right here, but this oxygen is neutral. So it's not exactly the same as the ion over here. And this is a carboxylic acid group. You don't need to know that at the moment yet. We haven't talked about functional groups, but I want you to just have a peek at this and understand that you have a methyl group, which you should know by now. It's just this carbon on the end with hydrogen saturating it. And then we have a carboxylic acid group. That's something you'll come to get used to, but aren't expected to understand right now, and that's all acetic acid is. It's about as simple as you can get, but it's called ethanoic acid. F means 2, and we have how many carbons? You guessed it. So let's look at what happens with the Bronsted Lowry acid, ethanoic acid. This highlighted hydrogen is going to make its way over to our alcohol, and it's going to create neutral water. Neutral water. So that proton is going to cancel out this negative charge by adding a plus. We're adding the pluses, y'all. And notice here the conjugate base is now a -1 formal charge on this end. So when you pop that hydrogen off, it left the electrons behind. And this oxygen became negatively charged. And it becomes a conjugate base. Why? Because it's going to accept hydrogen in. And the acceptor is the base. Bases, right? Okay, conjugate base. I think you get it from here. Should we look at maybe one more? I'll just come right over the top of it. This one, ammonia and water. Ammonia and water. Very common chemicals. Ammonia here. Circle the nitrogen. Do this with some practice, yeah? I see 3 bonds and 2 electrons, so that nitrogen is going to be neutral, and we can see over here while we're looking at it that we're going to only have 4 bonds here, no electrons. That's only 4 minus, and nitrogen needs 5, so that's going to be a +1 formal charge. That means that our base is ammonia here is going to accept this hydrogen from water. Okay, and I want you to remember that last time water acted as a base, now water is acting as our acid. It's acting to give a hydrogen. Bronsted Lowry acids donate protons yeah, and leaves behind this negatively charged oxygen, negative formal charged oxygen. Create this alcohol ion over here and create this positively charged NH4 ammonium ion. This is a really, really common thing in nature. Ammonium and ammonia are very important in the life cycle process. Nitrogen is what's necessary to make proteins in the world. Life depends on this reaction all the time. So again, notice something here, that water can be an acid or it can be a base depending on what you're mixing it with. That's the beauty of a perfectly neutral water like that. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.